Good morning, everyone, and welcome. We're getting started a few minutes late, but nonetheless, we are going to move along. We have a wonderful lineup of speakers for you today. For those of you who are joining us for the first time, welcome to UTPA. And on behalf of UTPA and the Office for Sustainability, we want to say thank you for joining us, and we're delighted to have you and hope that you will join us again. The Office for Sustainability was established about 2 years ago, and we started these educational workshops with the intent of educating our campus and our community on sustainable products, services, and practices. So thank you for joining us. Later this afternoon, we will show you a few other workshops that we have that will be scheduled here within the upcoming months. And you will have an opportunity to jot those down and to please contact us so that you can reserve your seats. As you can see, these are becoming more and more popular. Unfortunately, we have very limited spacing, so it's very important that you do make your reservations. And we thank you for doing so because, as you can see, you know, we're almost at a point of no seats this morning. Again, thank you. But before we get started, I want to give a special thank you to our annual donors. Again, as I mentioned, we've been doing this for the last 2 years, and we have some wonderful supporters. BBVA, Compass Bank, Innovative Block, and Lax Furniture have been with us from the beginning and have continued with us. So we want to say a special thank you to them for supporting us again this year. This workshop today, our sponsors are Schneider Electric, Parsons Roofing, Perry Mechanical Systems, the Rio Grande Valley Sustainability Council, and Marco Arredondo Incorporated. So we want to thank them because, as you can see, we have a wonderful breakfast, continental breakfast, and later this afternoon you're going to enjoy a wonderful lunch. So please join me in thanking our wonderful sponsors. Again, thank you so much for joining us. And our very first speaker is Mr. Jason King. He's a graduate from Texas A&M University with a bachelor's and master's degree in mechanical engineering. He worked as a mechanical engineer for 11 years, designing and constructing major commercial HVAC systems on projects including churches, schools, high-rise buildings, and major sporting arenas such as the American Airlines Center and the State Farm Arena. For the last 5 years, he has been a manufacturer's representative in HVAC products with Perry Mechanical Systems in Edinburg, Texas. Please help me welcome Mr. Jason King.
Hello? Better? Okay. As she mentioned, I'm Jason King with Perry Mechanical Systems, mechanical engineer, and done several years in the construction and design industry, and most recently I've moved into the equipment sales arena. Been doing that for about 5 years now. And today I'm going to be talking about LEED, sustainability, and energy performance. So, of course, what we're talking about these days is green buildings, and what we're trying to figure out about green buildings is how we can make them more comfortable, more enjoyable to live in, and also save us money on the back end and return to savings. Excuse me, it's been a little while since I've looked at this. The energy consumption in the U.S. is broken up here by sector on this pie chart. You can see buildings account for 49% of energy use in the United States, 22% on industry, and 28% on transportation. So buildings have a significant impact on the energy usage that we have throughout the United States, and it's something that definitely needs to be looked at. 77% of electricity consumption by sector is shown here. Building operations for electric consumption is 77%, industrial is 23%, and transportation is less than 1%. The previous slide was overall energy consumption, including gas products. So the impacts on U.S. building resources, 40% of a primary energy use, 72% on electrical consumption, 39% of CO2 emissions, and 13% potable water consumption. I apologize for reading some of these. These are not necessarily my slides. These come off of USGBC, so I'm not as familiar with them. On the global CO2 emissions by sector, buildings are number one, and then transportation and industry. So what a green building can do for you is you can reduce your energy consumption by 24 to 50%, reduce your CO2 emissions 33 to 39%. Water consumption can go down about 40%, and solid waste consumption can go down about 70%. We also, in a green building, the occupants are healthier and they're happier. In the U.S., people spend about 90% of their time indoors. And green buildings typically have a better quality of an environment. The lighting's better, the air is better, and it just makes people healthier and avoid issues with their sick building syndrome and other effects. So some of the benefits to having a green building is your operating costs will decrease, your building value will increase, your resale value, your return on investment improves, your occupancy ratio improves. If you're in a commercial building, you're renting out space, you have a better occupancy ratio, and your rent ratio increases. And your retention rate increases as well. So if we look at energy usage in a building in the U.S., this is back in 2006 study in this chart here. You can see space heating is about 20%, lighting about 17%, cooling about 12%, and those three compose about half of your building energy consumption. And then you look at the other miscellaneous components over here. You've got computers, ventilation, cleaning, cooking, refrigeration, electronics, heating, water heating. So your major part is your comfort conditioning and your lighting. And of course, this is going to vary by demographic, but this is an average over the U.S. We're going to have more cooling than heating down here. So how does LEED factor into this and your energy consumption? If you look at the LEED point system, about 30% of the points are related to energy consumption. So it's a major, if you're doing a green building, a LEED building, energy is one of the primary things you need to be focusing on in that process. You get 19 points for optimizing energy performance, which means exceeding the baseline levels of 90.1. You get 7 points for on-site renewable energy. And these are varying degrees of these points you can get. 2 for advanced commissioning, which is extremely important. 3 for measurement and verification. And overall about 31%. Now, I think 2 of the most important things up here are the advanced commissioning and the measurement and verification. If you don't commission your building, you don't know if it's performing the way you said it was going to on paper. And believe me, they don't always perform the way they say they're going to on paper. And then also commissioning them again in the future to recommission the building is very important. Every 5 years or so to go in there, go through the system, make sure it's doing what it's supposed to. The other thing, that's very important is the measurement and verification. Just because you commission it and it operates properly, you paid a lot of money for the design, and these people are saying, well, it's going to cost you $100,000 a year in your electricity to run this building. Well, they may tell you that, but is it? So you need to go through and do the measurement and verification process, and if it doesn't, you need to go back and figure out why, and get the system operating the way it should. And there's been some information out there. I forget where I heard this the other day. They were saying some of the most inefficient buildings out there are green buildings because they're not commissioned properly and they're not measured and verified. So if you just put it on paper and walk away from it, a lot of times there are difficult or complex control systems, and if they're not commissioned properly, they don't operate properly. So now I'm going to go in, break down the energy consumption a little bit more and how we can attack it and become more efficient in our buildings. And I'm going to base this on a typical elementary school. Down here in the valley, mostly what we do in construction is schools, so I thought that was a good place to focus on. If you look at the chart of the energy consumption in a school, you've got about 60% for air conditioning, about 27% for lighting, whoops, about 8% on miscellaneous equipment, computers and so forth, and about 4% for water heating. So obviously the two biggest pieces of the pie you want to hit are these right here. And they're really the easiest ones to hit as well. So first I'm going to look at energy efficient lighting, and I'm not an electrical engineer, so these are things I've taken from other people and other sources, so I might be off on a little bit of this, but in general it applies. If you have high performance lighting, you increase your productivity. That includes task lighting or the right ambient light in the room, using indirect lighting so you get a good coverage instead of spotty lighting. So high performance lighting can increase productivity, 6.5%. And individual temperature control can also increase your productivity. And that's probably more applicable to like an office space. And if you look at LEED, they want every person to be able to adjust their temperature. You can do that either through a diffuser on the floor, or having little diffusers for each person, or having multiple zones. And when you have that ability to control your temperature, the person is comfortable and they're able to work more productively. So this is a little messy, but it's going overview of kind of lighting savings here. If you look at what kind of the energy code requires on a watts per square foot basis, you're going to be at about 1.2 watts per square foot. Now, that translates into about 0.4 cents per square foot per year in energy consumption. So a lot of the designs these days go a little bit beyond the 1.2, and they go to about 1.0 watts per square foot. So I'm going to use that as kind of a baseline. Now, if you go to a high efficiency lighting system, maybe a T12 or something like that on your lighting, you can get down to about 0.65 on your watts per square foot for the building. And in doing that, you can also lower your maintenance costs because you've got fewer bulbs to deal with. So you get dual benefit there. Your payback in doing this is less than a year. It's extremely quick payback, and in most new buildings, it just doesn't make sense not to do something like this. And there's also newer lighting technologies out there, such as the LED lighting, which is starting to kick on. And they're using it a lot in the gymnasiums now. I'm not real familiar with it. From what I hear, the paybacks are around 5 years on that. But again, the life of that lighting system is much longer than the traditional lighting system, so you get that benefit as well. I hear they're using LED lighting in other sources as well, but I'm not very familiar with that. Lighting controls is also very important. It's also a code requirement these days. So in order to control your lighting, you can do it through occupancy sensors, or you can do it through a centralized control system, which can integrate in with your air conditioning controls as well. So you can schedule lights on and off as necessary. But occupancy sensors are very inexpensive and a great way to automatically control lighting. So here was that pie chart again, just showing the 27 and 61%. And if we're going to go into that was supposed to show the reduction there, but I don't think it did. No, got the wrong slide on there. Now we're going to start talking about the air conditioning side of things. If you look at what I call a diversified and a non-diversified load, a lot of the calculations that engineers put out on the street, they don't diversify their load. And what a diversified load means is you take if you don't diversify your load, you would take the load on this room and the next room and the next room and add them all up. And if you do that, you end up with a lot more overall capacity than you really need on a building. For a diversified load, you would take the building as a lump sum and run a load on that for your maximum amount of people and your maximum amount of ventilation you would need for that building. And if you do that, your overall tonnage on the building will drop about 20%. So a lot of the buildings we see out here these days are grossly oversized, 20 to even 50%. So I'm not going to look at this non-diversified load because it's just not accurate as far as your energy consumption. And I'm going to look more at this chart here, which is a diversified load. And the biggest part that gets reduced when you diversify your load is your ventilation air, because your people, if you were to do that, adding them all up in a school, your kids are not in the classroom at the same time they're in the gymnasium and the band hall and the cafeteria. They move around the school. So if you've got every room full of people and maxed out on ventilation, you can just imagine how oversized your system's going to be. So with this diversified load on an elementary school, it came out to about 157 tons. And then here's the breakdown of where that comes from: your ventilation, your people, your miscellaneous equipment, lights, glass, walls, and roof. So first I'm going to attack kind of your skin loads, which would be your actual building, your roof, walls, and windows. About 10% of that is glass. And glass is very important because it has a major effect also on comfort. And if you're looking at LEED buildings, they want you to have a lot of glass so you get the daylighting and views credits. And there's a lot of benefits to having glass because of the indoor environment that it creates. The downside of having glass is the solar gains you get in the room. So there is a code on a minimum performance of glass for buildings in Texas. It's in the International Energy Code. And I would say I have seen several buildings in the Rio Grande Valley that do not meet code on glass. And nobody enforces it because nobody knows any better. And these architects say, well, we've always done it that way. Well, that's great, but that was 70 years ago. You were doing it that way. It's a newer time now. So if you have a single pane glass on a new construction building, it does not meet code. You have to go to double pane glass. You have to go to shading coefficients that are high performance so you don't get those solar loads. This can make a huge effect if you've got a lot of glass on your building. So glass is very important. And also, if you've ever been in a building with a lot of glass and it's bad glass, you really can't cool it because that radiation effect, you cannot get rid of that effect with air conditioning. You're just going to keep blowing air on people and it's not going to be comfortable. So again, this is talking about the solar code, and ASHRAE 90.1 is the standard for energy consumption that a lot of the codes are based on. And LEED is using that as their baseline, as well as the International Energy Conservation Code. So again, it will dictate what your solar heat gain coefficients have to be and your U values, which correlate into how many panes of glass you have and the shading. So as I mentioned again, there is a performance criteria that is required by state code, and I encourage you all to learn what that is and find out more about it. And in your buildings, make sure that you're getting that from your architects. And as far as educating the architects and your customers is to tell them to talk to somebody so they get a proper specification. Because they'll also, I've seen specifications where they say, well, just meet code. Well, if you tell somebody to just meet code and you don't really know what the code is, it's not going to happen. Because their specification will conflict with each other because they've got a specification that says meet code, but they're describing a piece of glass that doesn't meet code. So the glazing impact, if you've got 31% glass on a structure and your code minimum glass is going to, the cost of the glass is going to be the effect is going to be about 6% of your air conditioning load. The cost of the glass is about $1.25 a square foot, and the energy cost associated with that is about 5 cents per square foot. So if you have, again, we talked about benefits of more glazing is the better daylighting and the comfort and the increased performance of your occupants. But if you do that, you need to have the right kind of glass to go with it. So if you go above and beyond the minimum code glass, your air conditioning load will drop, your tonnage of your equipment will drop, and the cost of glass is not really that much more expensive. It might be 20 cents per square foot on a building, which is not a very significant impact on your building construction. The energy savings can be 3 cents a year, and the HVAC system can be reduced as far as the cost there as well, up to almost 40 cents per square foot. So it ends up washing out. If you take the savings out of your air conditioning system and put that towards your glass, you're going to have an immediate payback on this. So on a typical double pane glass, the solar load accounts for about 13% of the air conditioning, and this would be one that doesn't necessarily meet code. So it's going to add 10 tons to your building. The savings on your glass might be 25 cents a square foot, but your additional cost on your air conditioning is going to be 75 cents a square foot. So you're not getting anywhere. And then if you get a building inspector that happens to know what he's doing, which doesn't happen all that often, but if he comes in and sees that your glass doesn't meet code, then what are you going to end up having to deal with? Are you going to have to take that glass out and replace it? And what's the expense involved in doing that? I apologize. Are there any building inspectors in here? If you are here, thank you for being here, because I hope that more education is coming out to our building inspectors. And if anybody is involved in any of the inspection groups, I'd be happy. I would love to get involved with them and help educate, because there's a lot of areas that are not covered in our building codes that need to be covered, and they get overlooked all the time. So on the HVAC load here, we're looking at it again with some better glass in here. So our pie is changing a little bit as we go along. And as you can see, the biggest part still here is the ventilation. So how do we address ventilation? The code for ventilation is in ASHRAE as well. It's ASHRAE 62.1. And on a typical classroom, you're looking at about 13 to 15 CFM per person. They've revamped the code. It's not just a flat CFM per person anymore. It has to do with the square footage of the space as well. So the benefits of having more ventilation is your people are more comfortable. You don't have high CO2 levels, and high CO2 levels make people start falling asleep. So obviously not a good thing in a classroom. So if you increase your ventilation, you get a healthier building, you get better performance out of your students, you get better test scores, which is going to increase the performance of your school and also your funding for your school. And you're also going to have healthy people, which means fewer sick days and lower turnover in your teachers. So all of those benefits are huge, especially in a school environment where your funding comes based off of your attendance. So this is another USGBC slide here, talking about green buildings and occupant comfort. And in fact, I think this is the same slide we saw a second ago. 90% of our time is spent indoors, and green buildings typically have better environments. So learning the benefits of green schools results in increased productivity, increased learning and performance, and a decrease in teacher turnover. So how do we deal with ventilation and the costs involved there? Ventilation is just a huge component on any school or any building with people in it, and it's one of the more difficult things to condition in a building as well. Because if you don't condition raw outside air properly, especially in the Rio Grande Valley, you're going to be bringing a lot of humidity into the space, which is going to create mold and other issues. So it's very important that the ventilation is brought into the building properly. Now, if you do not include energy recovery, you're looking at about 36% of your air conditioning load. And the energy cost expenditure is about 27 cents per square foot in doing so. And where does that go? And how do we get it back? Well, most of your ventilation, you're bringing it into the building, so you got to get it out of the building. And a lot of it goes through your restroom exhaust, your janitor closets, locker rooms, kitchen hoods, trash rooms, and then whatever else is left over goes through your building relief. Most engineers will have either an exhaust fan or a barometric damper or something that if the building gets too pressurized, it's just going to relieve that air out of the building. And if they don't put that in, it's going to go out the door when it opens, so because it's going to be positive. So there's some air that is just going to be lost, and especially in a kitchen. You can't take the air coming off of your kitchen hood and recycle it into the building. It's just not suited for that. So in doing that, some of the things you could think about as a program planning for like a school district is the benefits of having like centralized kitchen versus individual school kitchens. If you have a centralized kitchen for the district, you take that unrecoverable exhaust air out of each building and centralize it into one location. You also can centralize your labor and expenditures into one location as well. So that's something, just on an overall planning thing to think about. Your about 20% of your ventilation air ends up having to be wasted in a typical school if you've got a kitchen at the school. So with the other air that we can recover, what can we do with it? We can bring it back into the building through energy recovery. And I'll give a little diagram on this in a second, but when we do this, we can get about 70% effectiveness out of this equipment. And what happens is you take your exhaust stream and pass it by the intake stream and recover that energy before it exhausts out the building. Now, obviously, you don't want to cross all of the air over because you don't want those contaminants that you have to exhaust out of the building. But there's the heat exchangers that do this transfer, which is why it's only a 70% effectiveness instead of 100%. So, 67% of your ventilation air is a viable candidate for this. So when you reduce your ventilation costs by 50%, you're looking at about 14 cents a square foot in savings you can get on your building. And if you don't even consider the benefits to your air conditioning system decreasing in size, you're looking at an increased building cost of about 60 cents per square foot, and that comes out to a payback of about 4 years. Now, if you take the load credit, which if you're going to recover this air, you can decrease the size of your central plant. So in doing that, you're going to end up with 18% less capacity on your overall building tonnage. This will decrease your building cost by $1.74 a square foot. So it's an immediate payback. Your actual cost is going to go down by including this type of technology. So this kind of shows a diagram of how it works. You bring your return air from your building, take it through, this is a wheel type heat exchanger, take it through one side of the wheel, exhaust it out, bring your return air back, or your outside air through the other side of the wheel, and it cools down because this air is transferring, the heat from this is transferring over to this. There's different kinds of heat energy recovery, and in our environment, the only one that really makes sense is true energy recovery or enthalpy recovery, because you want to recover the latent load as well as the sensible load, which means the humidity as well as just the heat. And not all technologies that transfer heat will allow that. So typically, if you're going to be doing that type of system, you're going to be using a wheel. So now I've revamped my pie here. My ventilation's decreased considerably, and now my people and my miscellaneous equipment are a much bigger part of the pie. And we can't necessarily do anything about the people, because they got to be there. Our miscellaneous equipment, that's our computers, our overhead projectors, things like that. There's not a whole lot we can do there. There are ways to advance in those departments, and some LEED buildings have actually gone to the extent of having dual receptacles in their buildings. So you have one set of receptacles that's for 24/7 operation, and another set of receptacles where you can plug in your computers and projectors, things like that you're only going to use during the day. So at 5 o'clock in the afternoon, all those receptacles are just automatically shut down, and all of the power is saved on those. So it's kind of a neat strategy in your electrical design. Of course, there's added costs in doing so because you've got to run more circuits and more receptacles for that. So now we're looking at also the percentages here. Our air conditioning is at 60% of the load now, lights at 25%, miscellaneous and heating at 15%. So how else can we improve our energy consumption? Well, now you have to start looking at the HVAC components on an individual basis. And if you look at a traditional ranking of systems as far as efficiencies go, this is kind of what you'll find. Your water-cooled chillers are typically going to be your most efficient. And you usually don't, most buildings, kind of the cost break point is about 500 tons as to when you jump from air-cooled to water-cooled. Now that needs to be analyzed a little bit more if you're looking at a life cycle analysis of 25 plus years, especially in our environment, because the air-cooled equipment's sitting outside and won't always last as long as the water-cooled equipment. So if you factor in the cost of changing out an air-cooled chiller versus not having to change out a water-cooled chiller, then it can make sense to go water-cooled at a lot smaller tonnages as well. Kind of the next technology as far as efficiency would be variable refrigerant volume. This is a fairly new technology to the United States. If you go throughout the world, it's the most common air conditioning system used throughout Europe and Asia. It's extremely efficient, and the reason we haven't seen it so much here is kind of our typical old American mentality is efficiency doesn't really matter. I just like, my systems the way they are. But, people are starting to see the costs associated with their energy bill, and these systems are really beginning to catch on. So that's kind of the second in the line of energy efficiency. And even overseas, though, on the really large buildings, they're still going water-cooled. But you're talking even well over 500 tons till they typically do that. The next would be the air-cooled chillers, and then your packaged DX systems and your split DX systems. Now, can this change? Yes, it can, because there's new technologies coming out all the time that will change how these things stack up against one another. This is a little bit of a busy slide here, but if you're looking for more efficient air conditioning equipment, I've kind of shown a chart here with the overall costs from this is a 300-ton project for 2 chillers. If you look at traditional air-cooled chillers, traditional water-cooled chillers, and then what I'm calling a premium efficiency water-cooled chiller, which would be some of these newer technologies that are out there. There's magnetic chillers out there now, which the shaft levitates on a magnetic field instead of having oil lubrication in the system. And in doing so, you reduce those friction losses. And in doing so, your efficiency obviously increases as you do that. And then the other system I'm looking at here is the VRV system, which is the variable refrigerant volume we were talking about. So if you look at kind of your operating costs on this line and your payback right here, and I have factored in some maintenance costs in this, so it's not just energy based. And also on the water cooled stuff, I've also factored in the water treatment costs, because that's a significant impact on a water cooled system. So your traditional water cooled system is our baseline. A traditional, air-cooled system, a traditional water-cooled system would really never pay back in a 300-ton range unless you're looking at the replacement cost of that air-cooled chiller as being more often than your water-cooled. These premium efficiency, like a magnetic chiller, you can get about a 10-year payback, and you're also going to get the benefit of having that equipment last longer. So even though 10 years is not always that attractive to a building owner, if you're looking at the additional capital investment down the road, it can become a lot more attractive. The VRV systems are, like I said, are extremely efficient, and their costs are not as extravagant as having to go to a water-cooled system. So you're looking at about a 4-year payback on a VRV type system. This is showing a little bit larger building here at 500 tons. And looking at a little bit different mix of equipment as well. When you get into the larger tonnages, there's some different products that are available out on the market, so there's some different things we can look at. If you look at the traditional air-cooled chillers as the baseline, then you go to, there's some newer air-cooled machines out there that their efficiencies are, when you look at them compared to a traditional water-cooled machine, your overall operational costs are very close. Actually, they're more efficient because your water treatment is so high on a water-cooled machine. Now, again, the drawback is the longevity of the machine versus the water-cooled. But you're looking at a 2-year payback on these extremely high-efficiency air-cooled machines. Now, the downside is they don't start making these things until you get up to about 200 tons. So the next line here was your traditional water-cooled type equipment. You're looking at a 17-year payback, which is quite a long time. Now, if you go to a traditional water-cooled machine with a VFD on it for your improved energy performance, now you're getting into the 9-year payback range, which that makes sense, and especially when you're looking at the longevity of the equipment. And then here again is that premium, the magnetic type chillers here, where you're going to about a 7-year payback. And then also at the end here, I've shown the VRV system. On a large system, it's kind of just keeps that same kind of payback because it's a modular style system. Now the drawback especially on a larger building like this on a VRV system, it's going to be like dealing with a bunch of little split systems as far as the maintenance goes. So you're going to have a lot more filters to deal with, a lot more individual components to deal with. So for a lot of institutional customers, they don't have the staff to deal with those multiple pieces, and they like the centralized systems, which is why a lot of times we push towards a chill water system in our environment. But on smaller buildings, the VRV type system is definitely something that should be evaluated. So what are some of the issues with air-cooled chillers? Again, I talked about this as a shorter life. Typically, they're going to only last about half as long as a water-cooled machine will last, because a water-cooled machine is indoors and it's a more robust technology. Now, the other side of a water-cooled machine is you're going to have cooling towers, and the cooling tower is going to have to be maintained and probably replaced at about 15 years, just like an air-cooled chiller would. So that offsets a little bit of that incremental cost. Some of the cost effect, how can you avoid some of these additional costs? Well, most people down here will coat their coils on their chillers just because of our environment. They start degrading very quickly if you don't coat them. And then also, if you're going to invest in a chiller that's got this type of performance, you also can coat the whole chiller if it's going to be sitting outside. So you can put a nice coating on it that gives you the corrosion resistance that you need for our environment. This is showing kind of a comparison of what type of technologies are out there for air-cooled chillers. This line right here is the minimum required by ASHRAE, by our energy standard. As you can see, most chillers fall in this lump down here. These are, you can see blue lines is one manufacturer, yellow's another, and red's another. Each different color is a different manufacturer's offerings. So typically, most manufacturers have two offerings. One's going to be your standard efficiency one, which is going to fall, right down here at the bottom, and then they have what they call their high efficiency model, which is going to be up in this range. You're looking at, 13 IPL. Well, these are IPLVs. 13 IPLV or 15 IPLV, kind of as your ballpark numbers. The newer technologies I'm talking about on air-cooled chillers, you can see are dramatically more efficient. You're 48% more efficient than a traditional, minimum chiller, 27% more efficient than the typical high efficiency machine. So when you get into this range, you're talking about performance that can really make sense on an air-cooled machine. Now the downside is if you tell your design team, I want a high efficiency piece of equipment, they're probably going to give you one of these right here because that's what everybody has and they don't want to rock the boat. They're just going to go with something that's in this range. So if you really want to go for premium efficiency, you have to make sure and stay on your design team to make sure you get what you're looking for. Now here's a comparison. This was based on a Houston building. It was an overall life cycle analysis of an office building in Houston. It was about 400-ton office building. And it looked at the different types of systems here. We had a standard air-cooled machine, and I'm looking at these dollars per ton are your installed mechanical system dollars. So you're looking at about $3,500 a ton, or $11.67 a square foot for your mechanical system installed. This doesn't take into effect any electrical costs. This is purely mechanical. So obviously, as you get more efficient, your electrical costs really should come down a little bit as well. But you're looking at $11.67 a square foot, and you're about 800,000 kilowatt hours of consumption on this building with your traditional methodologies. If you go water-cooled, you're looking at $4,000 a square foot. It's going to add about $500 a ton, or $13.33 a square foot. Now, if you go to one of these premium efficiency air-cooled machines we were talking about, you're actually less expensive dollars per ton than you are water-cooled. So it's lower installed cost, and you're even more efficient. You see, you're almost half the efficiency of your baseline, and you're at $12 a square foot on your building. So, and this here is your condenser water side of the water-cooled machines. So you can see just the chiller is about the same efficiency on the water-cooled versus the air-cooled. The only way to really improve energy-wise over this is to go to some of the newer water-cooled technologies, which are like the magnetic machines. And then you get into a realm over here. But again, you're going to be even more expensive than this one here. because you got to pay for that additional water-cooled infrastructure plus the additional technology. But it's still, you're looking at a significant improvement. If you're looking at water-cooled machines, you're looking at a significant improvement, so it definitely makes sense. So some of the things we've talked about already as far as water-cooled machines go. You're going to have a higher maintenance cost that you have to deal with and more qualified technicians. But most of our institutional buildings that are dealing with these size systems can deal with that. You're dealing with higher water treatment costs. And this amazed me. When somebody told me these numbers, I had to go verify them myself. And I checked it out 2 different ways, and it was true. On a 500-ton system, say a middle school, the cooling towers, which are what cool the chillers outside, they evaporate 13,500 gallons of water a day. That's a swimming pool. Every day they evaporate. So when you're looking at LEED and being a green building, you also have to consider the water consumption side of things. And there's things you can do to help recover that. And down here, I mentioned that is, I know the new McAllen Library, they have a system installed, or at least it was an alternate on the plans. I don't know if they bought it or not. But they have tied all the condensate that comes out of their air handling units together and piped it back to the cooling tower to make up the water at the cooling tower. So now, where they might be at a negative 13,500 a day, they might be at a negative 10,000 or negative 3,000 a day. So they're never going to be at an equal basis, but they'll be able to recover a lot of that water that's lost. And the added benefit by doing that is the water they're putting back in the tower is colder, so the chiller is going to run more efficiently. And it's cleaner as well, so it's going to need less water treatment. So the other items associated with that are your water treatment costs and your your water costs and your chemical costs. This was based on McAllen water rates. So you're looking at almost $11,000 a year in additional cost on a 500-ton water-cooled machine of maintenance of just the water side. Let's see. So here's a summary of my technologies, and I got this off before I filled in some of it. So this is a summary of the different ideas. Looking at your skin loads, colors is very important on your skin loads because of reflectability, and I'm sure some other people know a lot more about this stuff than I do. But just changing the color of your building can give you an immediate payback. You've got energy efficient lighting. We can look at less than a year on your payback here. LED lighting, you're probably looking, I'm guessing at about 5 years there. Again, somebody else is probably a lot smarter on that than I am. High performance glass. If you look at the reduction on your air conditioning system, it's going to give you an immediate payback on the benefits of putting in high performance glass. And same thing with energy recovery systems. They'll give you an immediate payback as well. Looking at some alternates on your air conditioning system, you've got your premium efficiency air-cooled machines can give you a 2-year payback. Some of the water-cooled technologies can give you 7-year paybacks on the larger systems. And then the VRV systems can give you about a 3-year payback. Now, I didn't have any slides in here on sort of the packaged type equipment, but there's also some new advances in packaged DX equipment, which would be your rooftop units like you see on a lot of the schools and stores around everywhere. There's kind of 3 levels of efficiency you can go with. You can get your traditional stuff, and I know Marco will talk about benefits of heat pumps versus standard just cooling equipment. So there's benefits in doing that. There's your high efficiency equipment, which is of course going to be a little bit of a premium always, but it's going to give you about a 3-year payback. So it really makes sense to go pay that extra for the high efficiency equipment. But there's also some new technologies out in this front as well, where they're making these variable volume as standard so that you get the added benefit of reducing your fan speed as well as your compressor technology, putting variable speed compressors on machines. They're going with higher efficiency motors, and they're getting rooftop units now that are 70% more efficient than baseline. So there's some very new and very efficient equipment out on the market now that that owners are starting to look at and really see the benefits from the paybacks. So now, this all sounds great. Why don't we do it? And probably the biggest thing is the building owners have to be educated about it, and they have to ask for it. And again, you can't just say, I want high efficiency, because that's kind of like saying, I want it quiet. Well, what does quiet mean? What does efficiency mean? There's degrees of quiet and there's degrees of efficiency. So you need to specify what exactly you're looking for. And then you also have to make sure that your design team enforces those specifications. There's one building we designed down here for a school district with one of these extremely efficient chillers on it. And the engineer had vendors calling him saying, I can't comply with that. I don't want to, it's not fair to me. And I understand that, and that is a concern for a lot of the engineers, is to have competition. But that's where the design team needs to structure the bid in a way that you at least have the offer to where I can pay for the additional to get the high efficiency equipment. You can do a base bid and an alternate where everybody can bid the base bid and maybe only one manufacturer can bid the alternate that's more efficient, but at least it gives you the option to buy that if you want that performance. But in this case, they designed around that premium efficiency that the owner asked for, and because they were getting complaints from some vendors, they said, well, you can just bid your standard high efficiency equipment. Well, obviously they're going to get the cheaper product because the owner had no say in it when it came down to the bid. So owners and architects and engineers need to speak up and educate each other on what's out there, and educate people on the benefits and the drawbacks. And part of that's going to be the lack of competition. Once you get to that level, your competition goes down. So the fear is adding costs if you don't have the competition, but that's where you can at least lay out the costs so that the people who make the decision on what to buy have the costs in front of them and know what the paybacks are. And the other thing you'll hear from engineers when you ask them, why aren't you designing high efficiency? They say, well, we've always done it this way. And again, it's another weak excuse to just keep doing the same thing we've always done so that we don't have to rock the boat. And this talks a little bit more about allowing competition, doing the base bid and the alternate. And why should we make the owner suffer? Because some manufacturers have not stepped up to the plate and designed the more efficient equipment. The stuff that's out there on the market is not proprietary items. They're technologies that other manufacturers can build. They just have not gone the extra step to invest in the R&D to develop it for themselves. So what do we do next? Do we just wait on the owner to decide to be energy efficient if you're a designer? Or do we talk to the owner and educate them on how to be more efficient? And do we design to what we know the owner needs over his building life? That's really the question that as an owner you need to ask yourself, what do I need? And as a design person, you need to ask the owner what they do need. So you want to do things that are going to make the equipment last longer. You want to put coatings on the expensive equipment so that it lasts in our environment. You want to, if you've got infrastructure on your cooling towers, you want to make sure it's galvanized. You don't want just plain steel sitting out there because it's going to rust and it's not going to last. You don't want your cooling tower falling to the ground. We want to design buildings to last many years, so we also want the heart of the building to last as well. And the other thing is, we put a lot of money into costs of things that make sense to us, which is like insulation. Well, the building code doesn't even require us to insulate walls. Now, it's a good idea. I'm not saying don't do it, but the cost of we'll put a lot of money into a lot of wall insulation, but we won't necessarily put money into our air conditioning system to get it more efficient. So just think about that when you got to think of your air conditioning system the same way you think of your other systems in your building. And the other thing is how can we offset some of these costs? Well, obviously your energy efficiency is going to offset it over the long term, but you might find ways in your building to offset some of these costs as well. And a lot of these technologies offset themselves. So here's the benefits, lower energy cost, lower maintenance costs, healthier buildings, healthy occupants, and improved comfort and performance. And then also, and I'm not real familiar with this, somebody else might be talking about it, I don't know, but there's state requirements out there now for schools and other public entities that they have to reduce their energy consumption. So this also helps you meet those goals that are state mandated. Let's see, got a little time. These are just some slides that I've pulled off the internet from the Green Building Society. There's 55 million students and 5 million faculty, and that makes up 20% of the American population. So schools are obviously very important, and how we treat those schools and how we live in those schools is very important as well. We spend over $35 billion? Yeah, $1 billion in tax dollars annually. So again, we need to be good stewards of that money as owners and designers, that we use that money in a way that it's beneficial to the people that are funding those projects. Green buildings will decrease energy and water costs, and student scores will go up. They did a case study of 30 schools that were LEED projects, and LEED is extremely it's caught on a lot throughout the U.S. I know it's fairly new around here, but a lot of the schools around the U.S. are going LEED as well, and some cities have adopted it as a minimum performance in their buildings to be at least LEED certified. And I know TSTC recently they have the first LEED Gold building at their facility now, and it's Chuck Smith, who is the building operator there, or the building engineer and manager of facilities, he said that they'll start reaping the benefits of that, going to that LEED Gold building in 5 years. So it'll start paying for itself, or paying them a dividend in 5 years over going with traditional technology. The average direct savings in these 30 schools were 33% in energy savings. The average indirect savings was energy savings was 50%, and the average water savings was 32%. So those are, that's some very significant numbers when you're looking at the benefits of going to a green school. So the direct savings for an average green school is $47,000 on annual direct energy savings per school, $95,000 annual total direct savings per school. Those are big dollars in your bottom line, and also as a lot of, I don't know how funding works for schools, but I know it's pretty convoluted. But we go out and get these bond elections, so we have a lot of construction dollars to build new schools, but we don't have money to maintain them. And we don't have money for the electrical bills, because it comes from a different pocket. So if we build those schools better and more efficient, then we can cut our long-term costs that come out of our everyday operating expenses. Also, we're going to increase the productivity when we do so with increased lighting performance and comfort performance. And that's going to help our kids get better test scores and be healthy and come to school, which is also going to increase our bottom line as a school district, because we're going to get our funding that way. I've gone through this slide already. The other thing I talked about a little bit with the ventilation is mold prevention. And that's very important, that when you bring in these ventilation systems, that when you bring in your outside air to your building, you want to make sure you do it right so that you don't have problems with your building. This is talking about green schools going up everywhere. There's 208 LEED certified buildings. This is as of September 2009. LEED certified schools, and 1,600 of them registered. So they were in the process of becoming buildings and getting certified. This is a look at a middle school, Homewood Middle School, 35% energy savings and 43% water savings. Fossil Ridge High School, I think that, Fort Collins, Colorado, 59% energy savings and 69% waste diverted. This is something called the 2030 Challenge that was put out by, I think it's the Department of Energy. And what they're talking about going is to a carbon neutral state by 2030. Today we're at 60% fossil fuel energy reduction with, this is the fossil fuel energy consumption, this is the reduction. 2015 they want to be at 70%, 2020, 2025 and then be carbon neutral by 2030. It's just a goal that's out there for people to strive to get to, and there's more information on it if you go to their website. This is from architecture2030.org. And I think that was the end of my stuff. So I guess, does anybody have any questions or comments regarding any of this?
You may have mentioned it, but I just wanted to ask again. For the premium water tower, what was the life expectancy? Did you say 15 years?
When you go to a water-cooled system, your chiller is going to last about twice as long as an air-cooled system, so you're going to have about 25 to 30 years on your chiller. Your cooling tower, however, is probably only going to be about 15 years. You're going to need to, at a minimum, probably replace the fill in it every 5 years, and probably replace the tower at about 15 years. Do you agree with that, Bill? You agree with that, Bill? Well, oh yeah, on your tower, you definitely go stainless steel or fiberglass, something like that. But I was talking about the galvanized as far as your supports. So, yeah, you don't want to use galvanized towers down here. You get about 5 years out of them.
I've replaced 2 of those supports.
Okay.
These figures that you have, these are just across the United States?
Most of them are across the United States. The ones that were in the tables, like the Excel spreadsheet stuff I pulled over, that was most of it was Brownsville based, some of it was Houston based. Anything else?
Any further questions?
Well, thank you all for your time, and